Welcome to Planet Earth for Educators. I'm Dr. Freddie Jo Breschke, and I will be introducing a number of topics in this series that are relevant to this class. Planet Earth for Educators focuses on earth science topics that you might find in a kindergarten through 8th grade classroom. This class is intended for those students who are pursuing a multiple subject credential to teach in their future classrooms. As such, we cover content that is related to the next generation science standards, so the topics that would be expected to be taught in a K-8 classroom. This also should help prepare future teachers for testing that they will need in order to get into credential programs. This class is designed to be hands-on. We work collaboratively on inquiry-based science questions related to these topics throughout the semester. The series of videos is going to address some of the content that is delivered in class as part of those activities. When we teach science, and when we learn science, it's a little bit different than other types of subjects. Sometimes students have told me that they feel like they're learning a foreign language when they start learning science. There's a lot of terminology to become familiar with. Sometimes students find that to be a little bit intimidating, but it's just a matter of learning these terms. There are a set of basic practices to master, like making observations and doing calculations, taking measurements. Inquiries, which are really the heart of doing science, can be confusing and frustrating if a student doesn't have enough base knowledge or if they're a little too open-ended. If inquiries, on the other hand, are too restrictive, if you hand students a cookbook, step by step, do this, do this, do this, and fill in the blank, they may not get as much out of the exercise as they would otherwise, and it can be kind of boring. So teaching science is really a matter of balancing between these two things, between allowing students the ability to design their own inquiries and perform them, and directing or guiding students toward your learning objectives and toward answers that help give them a base knowledge of science. When teaching science, even in the elementary school classroom, you should be prepared to go deeper with all topics. There will be students, even down to the kindergarten level, who get very involved in the science and may have questions or wish to do things that are beyond what you might have gotten in your own science experience, especially if you weren't a science major in college, maybe had minimal science exposure in high school. What the students will be expected to do in the next generation science standards in elementary school is probably very different than your own experience. So this course is actually partially designed to help you address that. Throughout the semester, we'll be talking about earth science topics. Earth science includes the study of earth materials and the earth itself. This is known as geology, and if you took a Geology 101 class or introductory geology class, this is what you most likely studied. So this would be things like rocks, volcanoes and hazards, plate tectonics, etc. Earth science also includes a study of astronomy, so stars, our solar system, planets, and the creation of the universe. In addition, meteorology falls under this rubric of earth science, so atmosphere, weather, climate change, and earth science includes a study of hydrology, of the water of our planet. By its nature, earth science is fairly interdisciplinary, so there are elements of chemistry and physics and math and even some biology present within it. So as you go to teach earth science, you will touch upon many of these other topics as well. 9 earth science literacy principles have been identified by the American Geoscience Institute and the National Science Foundation. These actually are seen within the next generation science standards, and throughout this course, you will see that we address pretty much all of these. I won't explicitly be talking about these in turn. As we progress the material, you will notice that we're discussing them. The first one we'll actually be talking about within the first week of this course, that this is about science practices. So making observations, making testable ideas, which would be hypotheses, and actually conducting those tests, which would be performing experiments. Please note that some of these involve the interaction of people with the planet. In particular, 7, 8, and 9 have to do with the way that people use the planet, the way hazards affect people, and then the way people affect the planet in turn, so changes that we make to the planet. So these are actually all within the next generation science standards. As we go more deeply and look at those, you'll see how these main ideas for earth science literacy fit into those standards. But to begin, the very first thing we need to address is what science exactly is. Science is a different way of knowing things, and what makes science powerful is that it is evidence-based. Science assumes that we can study natural phenomenon and we can actually explain how systems work because they're consistent and predictable. And that if we develop the right kinds of tests and collect the right kinds of evidence, we can form an understanding of those system models. But this depends on the fact that we always respect the evidence. So if we encounter some evidence that does not match with our ideas about how systems work, we don't reject the evidence or ignore that evidence. We actually modify our ideas about how systems work. So in this regard, science is always changing. Usually it's changing a little bit, and most people who aren't conducting the science themselves don't notice that it's happening. In the case of something new, for example, the COVID-19 virus that has appeared in the last couple of years in the world, the science, everyone gets to witness the science happening in real time, and it is very clear that things change as we collect new evidence. It's important to understand when you're teaching science that although science is changing, that does not mean that the science that we've currently got is invalid. It just means that it's always based on all of the evidence we currently have. So at any given moment, the science that we do explains everything based on our current understanding. So the current science is always the very, very best explanations that we have of the world around us. One of the first things that scientists do in what would be called the scientific method, but I prefer to explain as scientific thinking, is make observations. Observations are a critical part to the science process of experiment, but also the beginning part, the part you do before you develop an experiment, when you're coming up with ideas pre-hypothesis. So when you're looking at the natural world, what we always do all the time is make observations. This is one of the first science and engineering practices in the next generation science standard, which is labeled as asking questions. Observations and questions go hand in hand. Discrepant events are events that are a little unusual and cause you to ask questions and spark your curiosity. So for example, if I were to give a student a beaker that had water and dry ice in it, unusual things happen. Vapor comes out of the container and it sinks to the ground. The dry ice, which looks a lot like water ice that we're used to, sinks to the bottom of the beaker instead of floating. Bubbles come up within the water to the surface. All of those are unusual and not what we generally expect to happen with water, and would cause students to start making observations and asking questions. These discrepant events match up to the engage, or the initial part of the 5E learning cycle, which is a constructivist approach to teaching science lessons. The engage part is meant to introduce a topic by sparking curiosity and causing the student to have questions that they will then want to answer by continuing with the lesson. Observations can be many different things, and oftentimes in science classes there's a temptation to guide the students' observations so they make the right observations, so they look at the things that you want them to examine. But in reality, we all self-censor our observations. For example, in this example of the dry ice container, you might just be looking at the vapor rising or the bubbles, but not comment at all on the beaker. Say the beaker is see-through. Well, you expect that to be the case because it's made of glass and your mind immediately processes that. But that's also an observation. So there are many things that could be observations, and if you sort of guide the students too much, you might miss their ability to make some more interesting observations. On the other hand, prompting students so that they observe some of the things that you wish them to, that are part of the lesson, is often a good idea. So the trick is to get students to make observations about whatever your topic without putting words into their mouths. Observations, as I said, go hand in hand with questions. So making observations leads scientists to ask questions, and when you have questions, you then start making observations. So I might look at that beaker of water with the dry ice in it and have a question, like I make an observation, there are bubbles coming up to the surface, and I might have a question about that. What's causing the bubbles to come up to the surface? Is the water hot? Is it boiling? Or is something else happening? A hypothesis is a way to answer those questions. So I might have a hypothesis that, well, the dry ice is causing the water to boil, and that's what the bubbles are. So my hypothesis would be an answer to my question. My question is, what's causing the water to bubble? And my answer might be, the dry ice is causing the water to boil. As you probably know, that's not the case. That water isn't boiling. Those bubbles are actually gas that's being released by the dry ice, which is solid carbon dioxide that's releasing gas into the water, and those are the bubbles that we're seeing. You could easily test this by designing an experiment where, for example, you measure the temperature of the water. So that would be an experiment where you make observations that will test your hypothesis. But you're always going to start with observations and questions. And this is a great, observations and questions are a great way to introduce science within a classroom because you do not need a formal structure of an experiment or to develop a hypothesis. If you do turn a question into a hypothesis, the key is going to be to finding a good question. So you want a question that's both interesting, so it's not something we already know, and it's testable. You have to be able to come up with an experiment that will test whether or not the hypothesis is true. Otherwise, it's an interesting question, but it's not a science question. So there are plenty of non-testable questions, or questions you can't test with experiments. I can ask, is the container of dry ice scary? Is it beautiful? Those are questions that I can't answer by doing science, but they're certainly valid questions. Within this course, we'll be addressing science, so the way we conduct science within our science in particular, within the framework of the next generation science standards. If you haven't seen these before, they're pretty different than the science standards that had preceded them in most places. Certainly in California, the previous science standards were a list of factual knowledge, things that students should know at each grade level. The next generation science standards, on the other hand, are really more about things students should be able to do and understand. So they're very focused on students' activities and students' understanding systems. There's three components to this, which are called the three threads. You can see they're color-coded as blue, orange, and green. There are the content, which are DCIs. These are the content areas, and I'll be showing you those in just a moment. So this would be the parts of what you should know in the earth science, physical science, and biologic science, life sciences. There are cross-cutting concepts, which are bigger ideas that you'd find in all disciplines of science. So things like scale being important or noticing patterns are cross-cutting concepts. And then there are science and engineering practices. And the practices are things that scientists do. For example, scientists use computational thinking. Scientists make calculations. That's a scientific practice. And all of these are meant to be addressed by the next generation science standards. The way that they're established, you would look at a given content area in different grade levels, and as you progress through the grade level or the grade bands, your understanding and the complexity of the way you're addressing that topic will deepen. So for example, you might talk about the rotation of the earth and day-night cycles and the way we see the moon in kindergarten through second grade, and you're going to talk about that differently than you do in third through fifth grade, and again, talk about that differently than you do in sixth through eighth grade. But you'd address the same concept, the same general concept in all of the grade levels. It's easy enough to look up the next generation science standards, and later on in this course, we'll discuss them a little bit more. But just as a general introduction, these are the disciplinary core ideas, which is the content. And within each of these, there are subheadings. The earth science standards, as you can see, are in the middle. So you can see the first group is about Earth and the universe, which includes the universe, the solar system, and the history of planet Earth. Then Earth systems, so that matches up with that Earth literacy idea of the linkage between the biosphere and the geosphere. So this includes Earth materials like rocks, Earth systems like rock cycles, nitrogen cycles, carbon cycles, plate tectonics and large-scale interactions, so things like earthquakes and volcanoes, the role of water in Earth's processes, weather and climate, and biogeology, the relationship between the life forms on the planet and the geology. And the final category is the way humans and the Earth interact. So this has to do with resources that people use, hazards that we encounter, the way that people affect the Earth, so human impacts on Earth systems, and climate change. Some of the topics, specifically some of the topics within the physical sciences, also become relevant to study of the earth science. So you'll find that at the beginning of this course, we'll actually be addressing some topics within the Physical Science 1A standard, the properties of matter, as well as the Physical Science 2A standard, forces and motion, because both of those are important to understanding the solar system and the development of the universe. This is just blowing up those earth science standards, the core ideas, a little bit bigger so you can see them. Within each of these standards, there'll be a series of performance expectations. So these would be more specific and address a particular grade band or grade level. So for example, within ESS 1A, there might be a performance expectation for fourth grade that is more specifically something about the way the universe operates. As we go deeper into the material, we will start addressing those performance expectations. But as this is a lot to take in, I'll be addressing this slowly over the course of these videos. These are the science and engineering practices that are included in the next generation science standards. You can see asking questions and defining problems, making observations would be part of this, is the first one, developing models and using them, planning and carrying out investigations. So this would be making observations and performing experiments, analyzing and interpreting data, using computational thinking, constructing explanations, and the last two are about communicating results. They're about engaging in argument from evidence, so taking evidence and being able to develop a good argument to support an idea, and communicating this knowledge effectively. And the final part of the standards are the cross-cutting concepts. So these are just key words explaining them. We'll get into more detail about them. Patterns, cause and effect, scale, system models, energy and matter, structure and function, stability and change are the big cross-cutting concepts. Throughout the length of this course, I would invite you to think about the way that the lessons are put together, not just in terms of how they meet the science standards, but also how they fit into a 5E learning cycle for inquiry. So this is a constructivist approach that was developed in the late 80s that addresses how you can teach science, and it meshes very well with the next generation science standards. So you'll find in the course of the activities that we do in this class, there are pieces of it that meet each of these E's. The engage is the first one, and that is something that is provocative or interesting and causes the students to start asking questions that they want to answer by doing the lesson. So usually you'll start off a lesson with an engage, but just because it's at the beginning doesn't mean you couldn't have another one later on. And all of these, this little graphic makes it seem as if these are progressive, but really there's any order is fine for these. Explore is students actually conducting an activity that you provide for them. So usually it's fairly structured, although it doesn't need to be. And this would be the students conducting whatever it is that you'd like them to do. Explain is usually instructor-led. So this is where the instructor goes over the core ideas that the explore activity was addressing. And then extend or elaborate is students taking those ideas that they've learned from the exploration and explanation and applying them to a new context. This is where things get really interesting, and this is where you'd actually introduce your differentiation. And then finally, evaluate is assessment. So this would be testing the student's knowledge or mastery of the concept. It can be a test, but it need not be. It can be any activity that the instructor does not participate helping the students. So you would demonstrate their knowledge on their own. So remember, children don't have any preconceived ideas about how hard science is or how fun science is. So introducing science into elementary school age students is actually pretty easy. In general, they like doing it. They like doing experiments. They treat it as play. They naturally ask questions. And unlike college students or adults who are cautious about wanting to sound foolish or wanting to sound like they're asking questions that don't make any sense, elementary school age students will ask all sorts of questions without any self-consciousness. It's actually pretty easy to get them excited about science. So my hope is that by the end of this course, you'll feel like you have some tools that you can use in the classroom in order to make this happen.